less than 1.3. You're thinking we're still doing limits? You bet. Now we're going to talk about infinite limits and also limits at infinity. Two different things. Okay, think about that. Infinite limits and limits at infinity. Okay. Now, before we do that, let's do a quick review. I've got this function here, u, x minus 1 at the top, and you have a factor of x minus 1 at the bottom, x minus 2 all squared, x minus 4 all to the power 3. We know that from our pre-calculus 12 days that, yes, because we have a common factor of x minus 1, we have a hole or a point of discontinuity at, say it out loud, I want to hear you. That's right, 1. Now, I know you know about even numbers and odd numbers. I know you know about even and odd functions, because we talked about that in Unit 0. Did you know there are even and odd asymptotes? So can you predict what you think an even vertical asymptote would be then, out of the remaining 2 possible non-permissible values? And then can you predict which one do you think is the odd vertical asymptote? Now you're thinking both numbers are even, so that can't be the case, right? So where else can you look to see that there's a difference? Haha, the power. So the even vertical asymptote is at x equals to 2, and the odd vertical asymptote is at x equal to 4. Now, just to let you know what they look like visually, in the graphs below, we've labeled the vertical asymptotes as odd or even. So notice the even ones, they all go to the same point. So in this case, they both go up here to positive infinity, and they both go down to negative infinity. Where the odd ones, one side goes to negative infinity, the other side goes to positive infinity, and vice versa. Okay, that's why they're odd. So this is going to help us out when we're now going to talk about how to calculate infinite limits, where my y value, okay, so infinite limits means my y value now is either going to be infinity or negative infinity. So we have seen examples where a limit does not exist at a vertical asymptote. Such non-existent limits can be expressed as infinite limits if the vertical asymptote is even, because if it's even, we can say it's just positive infinity, negative infinity, or if you are finding one-sided limits. The problem with the odd ones, of course, the one-sided limits are not the same, so it still does not exist. Now the notation we do then is once again using the infinity sign or the negative infinity sign to talk about that limit value. Okay? So these examples below are going to make use of the knowledge of even and odd vertical asymptotes as well as the whole. So if you look at example number 1, I'm asking you, look at this. Oh, it's the limit as x approaches to 2 from the right. And notice that the factor here in the denominator, x minus 2, means that there must be a vertical asymptote at 2. And then because the power is 1, I know this is odd. So really, I know this is an odd vertical asymptote. Okay? So that means it differs from the left side to right side. But how do you still figure this out? Well, if I do a 2 plus, that's like me plugging in a number like 0 or 2.01. So on the top, you'll get something like 5.001 or so. And on the bottom, you'll get 0.001. And once again, 5 divided by a really small number is really a big number. So really, this equals to positive infinity. And just a note, this is an odd vertical asymptote. Okay? So therefore, knowing that this is an odd vertical asymptote and 2 from the right is positive infinity, number 2 says hits the same expression, but now 2 from the left. So without even doing any calculations, because I know this is an odd vertical asymptote, I can say that yes, the answer is negative infinity. If you do want to do some calculations, remember the number 2 from the left is like 1.999. So if you plug that in, you'll get like 4.999 at the top, and then negative 0.001 at the bottom. And lo and behold, this is why you also get negative infinity. Okay? All right, number 3. Notice that once again we have a vertical asymptote at x equals to 1, but because this is squared, we know this is an even vertical asymptote. So ultimately here, we know the limit from the left would be equal to the limit from the right. If I calculate the one from the right in this case, positive 1 from the right is like 1.001. If I were to subtract 2 off of that, I get what? Negative 0.999. And then 1.001 minus 1, that's 0.001. All squared is really small. This is negative infinity. Okay? Negative infinity. And then for number 4, it's the same expression as number 3, except now the limit is 1 from the left, so I know that because this is an even vertical asymptote, it must be the same as the side to the right, and therefore it's negative infinity. And you can double check this by plugging in a number. I guarantee this is equal to negative infinity too. All right? Now, don't just be blind and say, oh, these are all vertical asymptotes, because number 5, you're like, oh, yeah, there's a vertical asymptote at 2. Hold on. Remember, if you plug this in, you get 2 squared is 4. 4 minus 4 is 0. You get 0 over 0. That's not a vertical asymptote. It's a hole. So just beware. Don't just automatically assume everything is a vertical asymptote. You have to be able to really identify, first of all, if it is an asymptote or a hole. If this is a hole, this is like what we did last day. So here's some built-in review for you. And I hope you can now calculate this limit. Yes, it's actually the number 4, and that means you have a hole in the graph, not a vertical asymptote, but a hole at 2, 4. Okay? Infinite limits. Done. So, turning the page, what is a limit at infinity then? So if the graph of a function f of x actually approaches a horizontal asymptote to the left or to the right, then f of x is said to have a limit at infinity. And if the asymptote is the equation y equals to this number L, then the limit as x approaches infinity of the function f of x is equal to L. So a limit at infinity is really this part here, where x gets large. Okay. Now, how do we calculate this? Well, we really just do this by looking at n behaviors for graphs. What happens when the x value is really, really large? And for polynomials, well, for large values of x, the highest degree terms in the numerator and the denominator dominate all the other terms. And therefore, those are the only ones you really need to consider. Okay? So, if you're thinking about how to do this, well, here are some review examples. Can you find the horizontal asymptotes? This is from pre-calc 12 days. Yeah, we just said look at the highest power of x's. Yeah, and then we just want to simplify that. So what's 5x squared over 10x to the power 4? Sorry, 5x to the power 4 over 10x to the power 4. That's right, that just simplifies to 1/2. And done. That was your vertical asymptote, y equals 1/2. For part 7 here, ooh, look, x to the power 4, x to the power 5. We simplify that. And then we'll get 1/2, but you still have an x in the bottom. And now when I plug in infinity for an x in the bottom, 1 divided by 2 times infinity, that's still infinity. 1 divided by infinity is, that's right, 0. So you have your equation y equals 0. And then for number 8, we'll do the same thing. Highest powers, who cares about the rest? We get x on the top and 2 on the bottom. We plug in infinity. Infinity divided by 2 is still going to be infinity. So therefore, what do we have here? Y equals to infinity? No, we don't say that. We're talking about finding the horizontal asymptotes. We just say, hey, there is no horizontal asymptote. Now, number 9, 10, 11, can you look at them? The question is find the following limits. But really, the expressions are the same. 9 matches with 6. 10 matches with 7. And then 11 matches with 8. So we can just copy down the answers if you wish, and you can. Done. But if you want to do things properly, let me just quickly show you how to do it properly for one of the choices here. I'll do that for number 9. So, yes, like I said, the answers we know. The limit here is 1/2. It's 0. And for this one, it's infinity or does not exist. So that's done. We're done. Okay. Now, if you want to actually prove it or you like some algebraic representation, let me show you what we would do. Okay, I'll do that with number 9. So we'll take the limit as x approaches to infinity. I'm going to ask you to factor out the highest power of x in the numerator. So in this case, that would be x to the power 4. And we're having 5, and you're like, whoa, how do we factor this? Well, I'm taking negative 3x squared divided by x to the power 4. So that simplifies to 3 over x squared. Yes, the x squared is now in the denominator. And similarly, it's 2 over x to the power of 4. That becomes my numerator after I factor out the highest power. I want you to do the same thing now with the denominator, okay? So same idea, factor out the highest power of the denominator, which is x to the power of 4. And you're left with 10 plus 3 over x to the power of 4. Okay? And this is nice because the x to the power of 4 simplifies, so now you just have limit as x approaches to infinity, and on the numerator it's 5 minus 3 over x squared plus 2 over x to the power of 4. Denominator is 10 plus 3 over x to the power of 4. Great. And you're like, now what? Well, let me do a side note over here. What is the limit as x approaches to infinity of the function 1 over x? If you said this is 0, you're correct. What about the limit as x approaches to infinity of the function 1 over x squared? If you said 0, you are correct. If you said the limit as x approaches to infinity of 1 over x to the power n, where n is any whole number that equals 0, you are correct. So really then, if I were to now substitute in infinity into my expression, what do we have? Well, it becomes 5 in the numerator, minus, and then 3 over x squared, well, that's just going to be 0. And 2 over x to the power of 4, that's going to be 0. And then the denominator, that's going to be 10 plus 0. So you're just left with 5 over 10, which is really the simplified form of 1/2. Look, that is your answer. All right? Now, you can try this for 10 and 11, and I can ask you to do it on your own to verify, but that is correct. Okay? Now, if they don't ask you to do it the long way, then that's right. Don't do it that long way. Just look at the end behavior. So for number 12, if you look at the end behavior, what would that be? Now, make sure you're considering the highest degree terms. Okay, careful, not the highest degree factor. So really, what is my highest degree term? It's an x times an x squared, which is an x cubed in the numerator. Hopefully, you can see that if I were to expand this out, I'll get 2x cubed in the numerator plus blah, 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 blah. And in the denominator, I'll get, what, x times, careful, 3x all squared. 3x all squared is 9x squared. 9x squared times x is 9x cubed. We get a blah, blah, blah factor like that. So once again, if that was too fast, remember 3x squared. And then now we don't care about the terms that are less than the highest power. We know that we can just compare the highest powers. So that's 2x cubed over 9x cubed. Those divide out and you're left with 2/9. So therefore, done. That is your limit. Okay? Now, we've just considered rational functions. Yes, these fractions. And rational functions like these above have at most one horizontal asymptote. So the limit is the same whether x approaches to infinity or negative infinity. However, that's not always true for other types of functions. And let me introduce to you to now the radical function. And these frequently have two horizontal asymptotes. You're like, what? Yeah, two of them. So, looking at examples 13 and 14, they are the exact same expression, but one of them is the limit as x approaches to infinity, and the other one is x approaches to negative infinity. So my question for you now is, what is the comparison of the highest degree term in the numerator and the highest degree term in the denominator? And if you said the highest degree term in the numerator is really just 4x squared with a square root, you are correct, because that minus 3 doesn't make much of a difference. But what does this actually simplify to? If you said 2x, I'm going to say no, because really the square root of 4x squared is not 2x. It is true, it's 2x, but it's only 2x if x is bigger or equal to 0 if it's positive. It actually equals to negative 2x if x actually was a negative number. So this is actually a piecewise function. Or some mathematicians will say the square root of any function is actually equal to the absolute value of it. So the absolute value of 2x. And of course the absolute value of 2x is defined as what I have here as a piecewise function. So you have to be careful here, friends. Because now if I do number 13, the limit as x approaches to infinity, the numerator, of course, is the square root of 4x squared. over x. That simplifies to the limit as x approaches to infinity of the absolute value of 2x. And because I'm going for infinity, I'm going to replace the 2x with, yes, the piecewise part that is bigger than 0. That will be positive 2x. And then now I calculate, and I get the answer of 2. Yet for number 14, hopefully you can see what's going on now. Same business for the first part. This still equals to the absolute value. But now the question is, what do I replace the absolute value with? Whoops. And yes, I replace it with negative 2x. And when I simplify this, lo and behold, look, there is an actual asymptote at negative 2. Wow. So if you were to graph this out, which I'm not, but if you were going to do that, you'll see at infinity, the graph gets closer to 2, and at negative infinity, the graph gets closer to negative 2. So something like that. Strange. Strange. Okay, so 4 more examples here. This time I'd like you to use the end behavior of the function y equals to e to the x, an exponential, okay, to think about these limits. So think about what e to the x looks like and see if you can answer questions 15 and 16 right away yourself. Go! If you said for 15 that this equals to 0, I'm happy. If you said this equals to infinity, I'm happy. Because e to the x is this particular function. And yes, the limit as x approaches to negative infinity, getting closer to 0, positive infinity, going to infinity. Awesome. Knowing that, can you hopefully figure out the limit for number 17? And you're like, e to the negative x. What does that function look like? So let me just quickly write this down as x approaches to infinity of e to the negative x. And I'm going to ask you to evaluate these two limits separately. E to the x, hopefully you remember that looks like this. Whee! So when it gets closer to infinity, this just equals to 0. Beautiful. And how about the next one? Well, this is just a rational expression just from above, so I'll take the end behavior of that, which would be 2x squared over x squared, and that just simplifies to 2. So 0 plus 2, you betcha, it's 2. All right? And I'm going to leave 18 for you to try, because I think you can do this. Remember, the idea is end behavior. Which term dominates? Okay, so you try that, please, and then come back and check your answer with mine. See, I'm making you wait. Those of you who don't actually do this yourself, too bad. You got to do it now. Okay, here are my answers. You're like, what? Answers? I'm going to give you 2 choices. The answers could be 2/3, or it could be 0. Which one is it? Remember the idea? The term that dominates. So in the numerator, the term that dominates must be 2x squared. It's the highest degree term. Now what about the denominator? How do you compare e to the x with 3x squared? Which one dominates? Which one really is the one that matters when x is big? Is it the 3x squared that's going to be huge, or the e to the x that's also or going to be even huger, if that's such a word? And if you notice the graph of the two functions, yes, e to the x actually dominates and goes up to infinity much, much faster. So really the highest power, so to speak, of x, not really a power, but the term that dominates here is e to the x. And now if you plug this in, yes, this is big, but the bottom is huge, and so the answer is actually 0. Think about that one if you're still not too sure, okay? And then start working on the assignment to solidify your understanding.